Okay, so normally I would have like participation questions at this point, but not today. It's just not working. So anyway, please participate and then just write your answers down. And here, I'll just the table is important, okay? So please participate, write your answers down, and then we'll go over our answers. Just try to make sure everyone's doing okay on this stuff here. Okay, so let's start. So you're gonna have to figure out these total columns, so you'll need a calculator if you don't have one, okay? You have a quiz today, and you'll definitely want your calculator for that as well, okay? So let's start with a few basic questions. So we'll just say, so this is all with the preface of, I guess, if I select one person at random, what is, and we're gonna ask, selecting from that group, we'll say from here. So all of these, you'll have to do a little bit of work. This is where do you get your, I guess, news from or something. All right, so we'll put that up on the screen. I'll give you guys a few minutes to work through these questions, and we'll go over our answers. You can just leave everything in fractions. You don't have to, I mean, you can convert things to decimal, but you don't have to, okay? So we'll go ahead and we'll just start right here. Just pause the screen. All right, so first off, we got to fill in kind of our totals. So let me know if I did my math wrong, but I got 148, 102, 114. Over here I get 172, 192 for a grand total of 364. Yeah. Okay, and then so probability of men will just be, we look at this row total, 172, divided by the total 364. Okay. So far so good? Okay, local TV, we got 148. We're looking at the column total, 148 divided by 364, okay? All right, local TV given men. So what goes in the numerator? Or let's start off with the denominator. What will go in the denominator? So the given part goes in the denominator, okay? The given part goes in the denominator. So this is the denominator, okay. All right, so this, we'll put 172 in the denominator, and then in the numerator, we'll put what? 66, okay? Because it's got to be of these 172 people, 66 of them, I guess, get their news from local TV or something like that. Okay, and then what do we do for local TV given women? In the denominator, what will we put? 192, and in the numerator, 82. Okay, all right, and this last question, is being a male independent of watching local TV? How do we even go about answering this? What comparisons should we make? We need to compare, basically, all three of these values will be equal if they are independent, okay? So we'll compare probability of local TV versus probability of local TV given men, okay? And if these two are equal, they are independent, and if they are not equal, they will not be independent. Okay, so the probability of local TV is 148 divided by 364, which when I convert to decimals will be 0.4066, okay? And over here, local TV given men, 66 divided by 172, and when I convert that to decimal, I get 0.3837. And so, as far as we're concerned right now, we say these two numbers are not equal. So, being male and watching local TV are not independent. All right, is that good? All right, and make sure you do not mix up something like this. Okay, this is different from this, all right? These are not the same. This over here would be 66 divided by 148. Okay. So make sure you don't mix those up. And over here, basically the comparison is going to be probability of A versus probability of A given B. Okay. So the front part, the A and the A given B. Okay. Don't compare probability of A versus probability of B given A or something like that. Yeah. Question.
So in a statement like that, is the given one the variable that comes first then?
What do you mean by comes first?
Like male is the given there.
For this part, or?
No, the question is being a male independent of watching.
Oh, it doesn't matter. So if here I did local TV given male, okay? But and the only reason why I did that was because we had these answers kind of already figured out. But if you wanted to do compare this, if you wanted to look up probability of male given local TV, and then you would compare this against what?
Men.
Probability of men, right? Okay, and so you could do that, and you would come to the same answer. You would come to the same conclusion that they are not independent. And if we had a different data set where they were independent, whether you did this comparison, local TV versus local given men, or probability of men versus probability of men given local TV, you would also come to the same conclusion that they are independent. So it doesn't matter. I did it this way out of convenience, but you would arrive to the same conclusion had you done it a different way. And this is where we are right now. Later on, we will talk about the effect of randomness in all of this. And so here we are saying watching, 0.4066 is different from 0.3837. Because those numbers are different, we're going to say they are not independent. And I think that's fine right now. But later on, we'll start to ask questions and just say, well, this is what I observed in my sample, this random sample of 364 people. If someone else took a random sample of 364 people, is it possible that local TV ended up something like 39%, and the probability of local TV given men also ended up 39%? And then in that case, the two numbers are equal, and then we would say they are independent or something like that, right? So we can start to imagine, hypothetical situations like that. And so later on in the course, and there's only a few weeks left, we'll try to start to disentangle, what's the difference between independent versus non-independent and versus just what's happening because of random effects. Okay, well, great. You can expect to see questions kind of like this on today's quiz. And if you did well on kind of this example here, then you should be good for at least the chapter 5 stuff. Let me talk a little bit just about, because it's already the third week. After Wednesday, we're halfway through the course, and it just flies by in summer. So anyway, 1 week from today, you'll have your midterm exam. Okay, so that's next Monday. I know it comes up real fast. And so Monday's exam will cover up through this Wednesday's lecture. Okay, so I'm gonna wrap up chapter 5 today, and then maybe start chapter 6. Basically on Wednesday we'll get through chapter 6. If we've got time left over, we'll do a few review questions, and then on Monday you'll have a midterm exam. That's going to cover basically everything from chapter 1 through chapter 6. Okay, I don't know if I need to write that down. I'll go ahead and write it down. Okay, so Monday, August 26th, midterm exam. And that will cover chapters 1 through chapter 6, which basically is the normal distribution. And this is going to be, I guess, week 3, Wednesday's lecture. Okay. The midterm exam right now, I'm planning it to just be all multiple choice. Makes the grading easier for me. So we'll do it that way, okay? And then on Wednesday, after the exam, we'll start chapter 7, and my goal is to get through chapter 9 in the textbook. And I think that's good for a 6-week course. So that's what we'll do. Okay. Any questions about just kind of logistical stuff? We've been having issues with this online poll system. I don't remember what I wrote in the syllabus. I said part of it, part of your course grade is based on this participation, but it's not working. So I'll give you free points for a lot of it. I might take attendance manually one day. I kind of dread doing that, but we might do that. We might have a real roll call one day. Okay. So don't worry about this online poll stuff. That's not working right now. So there we go. Okay. Yeah, question? Or wait, that was not a question. Okay. All right. Okay, great. We'll keep going on then. All right, so we left off, so we talked about independence. Independence, we said that if events A and B if events A and B are independent, then the probability of A given B is equal to the probability of A. Okay. And this comes into play when we have kind of the multiplication rule. I don't know why we name all of our rules, but this is the multiplication rule. And this just says for any events the probability of A and B is equal to the probability of A times the probability of B given A. And then what we say is that if A and B are independent, then the probability of B given A becomes what? Just the probability of B, exactly. Okay, so if A and B are independent, then the probability of B and A becomes probability of B, and the probability of A and B is equal to the probability of A times the probability of B. Okay, and this can further be expanded, and if you have like if events A, B, C, and D are all independent of each other, then the probability of A and B and C and D is equal to the probability of A times the probability of B times the probability of C times the probability of D. Okay, so let's just do an example here. Let's see if this this makes sense. Okay, let's say I've got I don't know, a little jar. Okay, and inside the jar I've got some marbles here. Okay, and we'll say three are blue and the other 7 are green. Okay, so I've got 10 marbles, 3 blue, 7 green. Okay, and I'm gonna shake the jar. This is you can't see inside the jar, so I don't know, it's an opaque one. And then I'm gonna just reach in there and grab one marble out, okay? So shake the jar, grab one marble. Okay, So I'm going to just say, what is the probability I get a blue marble? Okay, so that should be easy. That should be what? 3 out of 10, right? 0.3. No surprise. Okay. So, so now we can have kind of different situations. So one is I could draw the marble and I could leave it out, okay? And then now I have 9 marbles left in the jar, okay? Or one is I can put the marble back in and we have 10, okay? So I just kind of want to show the difference between these things, okay? So remember the original rule is that the probability of A and B is equal to the probability of A times the probability of B given A, okay? So we're going to start by doing, we'll draw marbles what we call without replacement, okay? Which means we'll draw a marble and we'll keep it out, and so after I draw a marble, there's only 9 remaining, okay? So after I draw a marble, there's only 9 left, okay? So here's the question. What is the probability that I draw 2 blue marbles? Okay, this can be broken down to what is the probability I get blue on the first draw and I get blue on the second. Second draw. Okay, so we'll just say this is probability of blue first and blue second. All right, and anybody want to take a stab at this? Okay, so what is the probability I get blue on the first? What did we say? We said 3/10, right? Okay. Excuse me. Thank you. Okay. Okay, so getting a blue marble on the first draw, 3 out of 10. Okay? And then the thing is, what is the probability I get blue on the second given I got blue on the first? So if I've drawn a blue on the first marble, then my jar now has what? 9 marbles, and how many are blue? 2 are blue, right? Okay, so the probability of getting blue on the second will be 2 over 9, okay? And so we multiply 3/10 by 2 over 9, and we get 6 over 90, which I think is 1/15. Okay. Seems reasonable to me, okay? All right. Contrast this to what would happen if we did the drawing of marbles with replacement. Just want to make sure everyone's so far so good. Okay, so we've got this, and we'll say, let's say I draw marbles with replacement, which means I'll draw a marble, I'll look at it, and then I put it back in, so there's always 10 marbles in the jar, okay? So basically, I put the marble back, so there are always 10 marbles in the jar. Okay, so here I will ask, what is the probability of drawing two blue marbles? Okay, so this is going to be probability of blue first, and blue on the first draw, and blue on the second draw. Okay, so here we can do the regular rule, basically blue on the first times the probability of blue on the second, given that we got blue on the first. Okay, so this is, I think we wrote the same thing on the previous slide, because this rule is always true. But because I'm doing things with replacement, each draw is independent of the previous draw. Okay, so when I put the marble back, basically I'm undoing whatever happened in the previous draw. Okay, so if I got a blue marble on the earlier draw, I put that blue marble back, and we're resetting the jar so it's back to its original condition. So basically, what happened earlier has nothing to do with what's going to happen next. Okay, that's different from the situation where I kept the marbles out, where I did it without replacement. If I drew a blue marble, then what's left in the jar will be different than if I drew a green marble. Okay, so if I drew a blue marble, then I'll have 9 marbles, 2 are blue and 7 are green. But if I drew a green marble, then I'm going to have 9 marbles, 3 are blue and 6 are green. Okay, and so what remains in the jar is affected by what happened in the previous draws. Okay, so that's a situation where the draws are not independent. What happened earlier affects what's going to happen next. Whereas in this case, because I'm always putting everything back and I'm resetting the jar effectively, each draw is independent. All right, so basically, I did this wrong. This boils down to just getting probability of blue. Basically on the first draw, right? Just probability of blue. Okay, and so this will be, blue on the first draw is going to be 3 out of 10, and probability of getting blue on the next draw is going to be 3 out of 10. And so this will be 9 out of 100, or 0.09. Is this feeling okay so far? All right, let's keep the same kind of scenario here going. So again, 10 marbles, 3 blue, 7 green. And let's, again, pretend we'll draw with replacement. This will, so I'm gonna, I draw 2 marbles with replacement. Okay. All right, so now the question is, what is the probability I get blue on the first draw and green on the second draw? Okay, and then I'm going to ask a similar but different question. The other is going to be, what is the probability I observe 1 blue and 1 green marble in any order? Okay, go ahead and take a moment and see if you can answer these questions. Okay. And again, normally we would make this a participation quiz, and you would click buttons, but the online poll's not working, so pretend that participation points are on the line. But I'll be nice and give you all your participation points here. Okay. Okay, what do we have? Anyone want to just shout out an answer? 0. What's that? 2-1, good. Okay, and over here? 0.42. Okay, all right, let's go over these answers. All right. Probability of blue on the first and green on the second. Okay, so we want probability of blue on the first. Okay. And because they're independent, I can just go straight to probability of blue on the first and probability of green on the second, right? And I can even just scratch out the words on the first and on the second here, because they're independent, it doesn't matter, right? Okay, so probability of blue, 0.3, probability of green, 0.7, indeed, 0.21. Okay, I think we got this, right? Okay, so and so some of you, I imagine, wrote down 0.21 for the second question, and then you're wondering why it's doubled, okay? So here, the distinction here is that I said, what is the probability I observe 1 blue and 1 green marble in any order, okay? And so there's 2 actual outcomes here, all right? One is I get blue on the first and green on the second, which is a distinct outcome, which is different from getting green on the first and blue on the second, okay? So I'll say there's two distinct possibilities. Okay? Blue first, green second, and green first, and blue second. Okay? And it might not feel that they're different, but you know, maybe another example, which is very similar, is you know, a family can have two children, and one can be a boy and one can be a girl. But the family where the boy is born first and the girl is born second is a distinctly different family from the one where the girl is born first and the boy is born second. Okay, those are different situations. And so when we talk about getting one blue and one green marble, we have to consider all the possible kind of arrangements or the possible orderings of these things. Okay, so anyway, this is the probability of blue times the probability of green, which is 0.3 times 0.7, 0.21. And over here, this is probability of green first, so probability of green times the probability of blue, which is going to be 0.7 times 0.3, also 0.21. Okay. And I added these together. Why did I add these together? What allows me to just add them up together? Not that they're independent, but we had another term. They are mutually exclusive. Do you guys remember that? So what does it mean for events that are mutually exclusive? It means that there's no overlap between these two kind of outcomes, right? So in one outcome, we got blue first and green second. And if we got blue first and green second, there's no like overlap. It could not have happened at the same time as getting green first and blue second. Okay, so those are two distinct possibilities with no overlap. Okay, and so I can just add those two together. Okay, it's not like I forget what the example was that we did today. You know, male female versus local TV or national TV or something like that. Okay, you can. There was overlap there in terms of males and local TV and whatnot. Okay, but anyway, these two outcomes are mutually exclusive, so I can just add them up. And we get 0.21 plus 0.21, and we get 0.42. How do we feel about all of this? Okay, we'll continue building up on this and just ask more and more ridiculous questions. So this time, we've got 10 marbles. Same thing. All right, should have just copied. Okay, so we'll say 3 blue, 7 green. And this time I'm going to draw 4 marbles with replacement. 4 marbles with replacement. Okay, I will ask, what is the probability we get green, we observe 4 greens, okay? Okay. Okay. If you just had to write an expression with like a raised to some power, what would you write? So this will be probability of green times the probability of green times the probability of green times the probability of green, right? So we have to get green each time, and every time we draw, because it's with replacement, each draw is independent. So here I would get 0.7 raised to the 4th power. Okay, and I don't know, what is that? It's like 0.2401. I don't know. So where's the calculator? 0.7 to the 4th power. 0.7 to the 4th. Yeah, 0.2401. Okay. Okay, so we have that. Is that good? All right. What if I ask a different question? What is the probability we observe at least one blue marble? Okay, in 4 draws. Probability of observing at least one blue marble in 4 draws. This is a little tricky. Any guesses here? Okay. So when we talk about at least one, this means we can go with 1 blue, 2 blue, 3 blue, or 4 blue marbles. Okay. Is there any other possibility I'm leaving off? Okay. So when do we not get at least 1 blue marble? If we get 0 blue marbles, right? All right, so this is all the possible outcomes. We're either going to get at least 1 or 0, okay? And that's the universe of possibilities, okay? And whatever you're thinking, whatever event you are thinking of, this is it, okay? It's either going to happen at least once in your life, or it will happen 0 times in your life, okay? So you think of any event, anything that you want to do, achieve, accomplish, it's either going to happen at least 1 time, or it's going to happen 0 times. So you want to see a solar eclipse, it's either going to happen at least once, or it's going to happen 0 times in your life. There was a solar eclipse, the Great American Solar Eclipse of what? Was that last year or 2 years ago? I can't remember. 2017? Okay. Did anyone see it? Anyone travel to see it? Okay. I did too. It was like amazing? Or did you not think so?
I didn't travel, like it was, I lived like in the path.
You lived in the path of totality. Okay. Wow. All right. Well, congratulations. So, but did you at least look at the sky with your special glasses? Oh, okay. Well, rightly so. I recommend, I think the next one's coming up in, I don't know, a few years in North America. They had one in Chile like last year, but or like a couple months ago. But anyway, once in your life, at least, go travel to see a solar eclipse in the path of totality. So, all right. Are you from like Salem or something, or?
I'm from South Carolina.
South Carolina. Okay. So, where is it? I don't know. Okay. Well, South Carolina. All right. Well, welcome to California. So, all right. So we observe at least 1 blue marble in 4 draws, or we observe 0 blue. Okay. That's it. So, if we want this probability of observing at least 1 blue marble in 4 draws, we can say this is the complement of getting 0, right? So this is complement of getting 0 blue. All right, and what's the probability of getting 0 blue? So we can do 1 minus the probability of 0 blue. 0 blue is exactly the same as getting 4 green. So we can do 1 minus 0.2401. 0.7599. Might as well call that 76, but okay. So we got at least 1 blue is the complement of getting 0 blue, okay? Okay, is that good? This is all just probability rules stuff. All right, here, all right, we'll still go with 10 marbles, 3 blue, 7 green. Okay, we'll draw 4 marbles with replacement. All right, can I ask you guys to keep your voices down, please? Thank you. Draw 4 marbles with replacement. And now I'm going to ask, what is the probability I get 2 blue marbles? 2 blue and 2 green in any order. Okay. All right, this question kind of sucks, all right? If we had to do it manually, because if I say in any order, we have to think of all the possible arrangements where we can get 2 blue and 2 green, okay? So there are, we have to think of all arrangements, which include blue, blue, green, green, blue, green, I guess blue, green, blue, green, green, blue. All right. Oh man. All right, I gotta think here. Green, blue, blue, green, green, blue, green, blue, green, green, blue, blue. Okay. Just make this a little neater. Okay, so there are 6 possibilities, 6 arrangements. Okay, what's going to be the probability of this first arrangement? Okay, we'll go 0.3 times 0.3 times 0.7 times 0.7. Is that good? All right, and what's the probability of the second arrangement? Okay, so just taking each one, the probability of blue is 0.3, probability of green is 0.7, probability of blue is 0.3, probability of green is 0.7. Okay, and then I can keep doing this. This one's 0.3 times 0.7 times 0.7 and times 0.3. Okay, and so on and so forth. All of these simplify to 0.3 squared times 0.7 squared. Okay, this is because multiplication is independent or not affected by the order of terms. Commutative, I believe, is the property there. They all end up being 0.3 squared times 0.7 squared. Is that good? Okay, and this would be the same for all 6. And so the total probability, because all of these are independent, I can just add all 6 of these together. And so the total probability is 6 times 0.3 squared times 0.7 squared, which I don't know what that is. .2646. Okay, so if you draw 10 marbles with a replacement, the probability that you'll get 2 blue and 2 green is about a little over 1 1/4. 0.2646. All right, does that feel okay? So if we said something like you're going to draw 10 marbles, and what's the probability you get 5 blue and 5 green? Okay, this suddenly becomes a nightmare, right? Because now you have to think of all the arrangements where you're going to have 5 blue and 5 green. All right, and there's like 252 of them. And it's, you know, you don't want to have to list them all out. So there's actually, there's a little thing that we can do to get this number of arrangements, okay? And this is, I'm going a little bit beyond what the textbook is covering, okay? But this is called a combination. Okay, and it's the number of arrangements of, we'll call these of k kind of successes. These are just the terms that they use out of n possibilities. Okay, so when we talk about 4 marbles and we want 2 blue and basically 2 that are not blue, this is n is 4 and k is 2. And we might call this, the way we write this is we write n over k in parentheses. This is, we call this n choose k. And the formula for this is n factorial divided by k factorial times n minus k quantity factorial. Okay. No need to memorize this. You probably have a button on your calculator that will do this, and if you don't have a button on your calculator that will do this, I'll be sure to include this little, at least this part, the NK, this thing, this, I'll provide this formula on any tests, okay? So anyway, if we do 4 choose 2, this would be 4 factorial divided by k factorial, which is 2 factorial, and n minus k, which is 4 minus 2, which is 2, is going to be 2 factorial. Is that right? All right, and so this becomes 4 times 3 times 2 times 1 divided by 2 times 1 times 2 times 1. And you basically get 6, okay? Well, I'll do it. 24 divided by 4, and you get 6. So this time, if I said we have 10 marbles, and we want 5 blue, which also means we want 5. Here, let's change this up. Let's do 4 blue. Four blue. Okay, so 6 that are not blue or 6 that are green. What would we write? We would have, what's our n in this time? 10, and k is 4, okay? And so we have 10 choose 4, and this is 10 factorial divided by 4 factorial and 6 factorial, okay? Okay, and you can do this, all right? So you could do 10 times 9, 8, 7, 6, 5, 4, 3, 2, 1, divided by 4, 3, 2, 1 times 6 times 5, 4, 3, 2, 1. And then, you know, these cancel out and those cancel, you know, this and that cancel, and you're left with something, I think 210 or something like that. There's probably a button on your calculator, depending on what kind of calculator you have. I only have the screen representation of this calculator, but I'll show it. Okay, so on my calculator, on this one, I can just do 10, and then above the division key, I've got an NCR button. Okay, so on your calculator, you might look for NCR. If you have a Texas Instruments, I'll give you instructions for that in a moment. So I would hit Shift, Division, NCR, and it puts this little C in there, and I put in 4, 10 choose 4, and it gives me 210. Okay. If you've got a Texas Instruments calculator, you'll probably need to click something like PRB. All right, if you got a PRB button, or you might have to hit like a math button and then use the arrow keys to get to the PRB section. And then after you hit PRB, you'll probably see NCR. Okay, and you can try this, and you can try 10 NCR 4 and see if it gives you 210. Okay. And if you don't, you know, you can always use this factorial, where you just have to multiply all the numbers down. Okay. Is it working for you guys? You guys find it? NCR on your calculator? Yes, no, maybe? All right, some of you guys are nodding your head, so that's good. And others of you, I'm not sure if you're paying attention, but we'll do our best, right? Okay. All right, so anyway, what was all this point? The point of this was so that we don't have to manually list out all of these arrangements ourselves, right? So if we just go back to our our original problem here, where we have, 10 marbles, 3 are blue, and 7 are green. And this time I'm going to say we draw 10 with replacement. Okay, and I will ask, what is the probability I get, we'll say 4 blue marbles in basically in any arrangement. All right, shall we work through this? Okay, so let's just start off with kind of one possible arrangement. Okay, so one possible arrangement will be basically blue, 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 and then green, green. 1, 2, 3, 4, 5, 6, 7. Okay, green, 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 green. Okay. And what will the probability of this exact arrangement be? Probability of this one arrangement is what? So I would raise 0.3, which is the probability of a blue. And how many times does this have to happen? So I would raise this to the 4th power, and I would multiply this by what? 0.7 raised to the 6th. Did I count wrong? I did. Wait. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I have an 11th. Okay, sorry. All right, 0.3 to the 4 and 0.7 to the 6. Okay, we want 4 blue out of 10 draws. So we have 0.3 to the 4 and 0.7 to the 6. Is that okay with everyone? All right, and now the question is, how many possible arrangements do I have? Okay. So, because I could scramble these all around, and I could say we're going to go blue, green, 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 blue, green, blue, blue, or something like that, okay? And as long as there are 4 blues and 6 greens, all of these, however I arrange them, can be simplified to 0.3 to the 4 and 0.7 to the 6, okay? And so the question now is, how many arrangements are there? How many possible arrangements are there where I have 10 marbles total and 4 are blue? So this is given by n choose k, and what did we say? So in this case, n will be 10 and k is 4, and this is equal to 210. Okay, question?
Are there still only 3 blue marbles in the jar?
Yeah. So, but we're doing it with replacement, okay? Yeah, if I did it without replacement, this is an impossible scenario, right? I can't suddenly make a 4th blue marble. But if every time I draw the marble, I'm putting it back, and so it's possible. It's possible to get a blue marble 4 times. It's technically possible to get a blue marble all 10 times. It's really unlikely, but it's not impossible. It doesn't have a 0 probability. Okay, but yes. So with replacement, yeah. Oops. Okay, so the total probability will be 210 times 0.3 to the 4 times 0.7 to the 6. Okay. You guys want to try an example? I'll give you an example and you guys work it out. Okay, so let's say this is not an investment strategy, but let's say you decide to buy, I don't know, we'll say 20 scratcher lotto tickets. Oh, maybe 20 is too many. We'll keep it simple, all right? So we'll do 10 scratcher lotto tickets, okay? And this is, all right, so these are like magic lotto tickets that, and we'll say the probability of winning any prize is like 10%, okay, which is much greater than it really is, okay? Buying a lotto ticket, if you learn one thing in this class, other than those 5 big points, the lotto is not the way to go. Gambling in general is all set up to benefit the person making the offer. Okay, so we're gonna buy 10 scratcher lotto tickets. The probability of winning any prize is 10%, and we will say, what is the probability of winning exactly one time? One time out of 10. Basically, one time out of 10. All right, you guys want to give that a try? Hit pause here. Okay, let's check this out. What's the probability of winning exactly one time out of 10? Okay, so what is one possible arrangement? Okay, will basically be 1 win followed by 9 losses. Okay. So the probability of this will be what? Probability of winning is 0.1, and this I will raise to the 1 power, okay? And then the probability of losing is what? 0.9, and I will raise that to the 9th power. Okay, and how many arrangements? So this is the probability of one arrangement. And how many arrangements do we have? 10, right? Okay, basically we have 10, choose 1, which is 10. So we're going to do 10 times 0.1 to the 1 and 0.9 to the 9. And what is that? 0.9 to the 9. 0.3874. Okay. What if I threw in, what is the probability of winning at least one time? Okay. So exactly one time means we only want to know what's the probability that just you win one and you have to lose all the other 9, okay? Probably we want to know what's the probability of winning at least one. At least one basically just means what's the probability I didn't lose all 10 tickets, right? So what is that going to be? So this is going to be 1 minus the probability of losing all 10, or winning 0. This will be 1 minus 0.9 to the 10. And what's that? 0.9 to the 10th power is that, and I will do 1 minus that number. I get 0.6513. Okay. How do we feel about this? Distinctions here between these two things, okay? Good? Okay, great. I think we will end our section on Chapter 5, Probability and stuff there. The book talks a little bit about simulation, and you will go over a little bit of simulation in your lab, but I will not put simulation questions on your exam. Okay. All right, and so now we'll touch on Chapter 6. We'll get started in Chapter 6, and we'll work through this. Okay. These are called probability distributions. Okay, so Chapter 5 is all about kind of probability rules, and we use these to figure out the probability of getting a particular event. And in Chapter 6, we kind of expand on this, and now we're looking at the probability of getting, I guess, certain outcomes, okay, certain numeric outcomes. So sometimes the outcome to a random experiment is a numeric outcome. Okay. And in those cases, we can say that outcome is a random variable. So, you know, if we pick someone at random and we say, you know, do they watch local TV or national TV or cable TV or something like that, that's not going to be defined by a probability distribution. Okay. However, if we said, I'm going to draw marbles out of this jar with replacement, if I draw 10 marbles, how many blue marbles do I get? Okay, how many blue marbles is a numeric outcome? Maybe I get 3 blue marbles, maybe I get 4 blue marbles or 6 blue marbles. So in that case, the number of blue marbles, the outcome to the random experiment, which is a number, that can be considered a random variable. And what we have is we have probability distributions. Distributions that basically tell us which outcomes are more likely than other outcomes. Okay. You know, it can be applied to categorical variables if you kind of make them 0 or 1. Okay, so if you've got a situation where you only have 2 possibilities, a yes or a no, you can make them 0 or 1 and turn it into a random variable. But basically, a probability distribution tells us which of these numeric outcomes are more likely or less likely than others. Okay. Okay, so here in our textbook, jump to page 1. Okay, so here's some book on Amazon. Okay, Lincoln in the Bardo. I don't know, never read it. Okay, this is the number of stars that the book received. Okay, so the people who left reviews, and again, Amazon reviews, it's hard to do like a true statistical analysis because we're not sure if, you know, what is the population, right? The population is, I guess, people who write reviews on Amazon, I don't know, or something. Okay, which I don't know who that corresponds to. So we've got, you know, 5-star reviews and 4-star reviews, 3-star, 2-star, and 1-star reviews. Okay, and this is an interesting thing. So a lot of products you got like all 5 stars and very few negative things, like your Uber driver. It's like if you don't give them a 5-star, that's like a fail, right? And so. But you'll get certain products, you know, especially if it's, you know, a book that's a little bit controversial or something, okay? You'll have people who love it, and then you'll have people who hate it, okay? And then you'll get stuff in between. So anyway, this will tell us, this is kind of a probability distribution. And so here, the questions you can ask about this are a little bit strange, but it would be something like, if I were to pick a random reviewer, because it's too much of a stretch to say this is representative of the population, we're going to just say, you know, if I pick one of the reviewers at random, okay, what is the probability they gave a 5-star review? Okay, and the answer is just 0.44. All right, so we have that. Here we can just say, if I pick a reviewer at random, what is the probability they gave a positive review? Positive is 4 or 5 stars. Okay, and so for that you would add 0.44 plus 0.15, and we get 0.59. All right. The values don't have to kind of be nice like this, like 1, 2, 3, 4, or 5. You can have situations where the outcome is, you know, spaced out a little bit strange, okay? So the textbook's got another example. Okay, so here is I'll just go ahead and we'll just put this in our notes here. Oops, don't want that. It says roll a fair 6-sided die. A fair die is one in which each side is equally likely to come up. You win $4 if you roll a 5 or a 6. And you will lose $5 if you roll a 1. Okay? And then for any other outcome, you will win or lose nothing. Okay? So the thing says create a table that shows the probability distribution for the amount of money you will win. Okay? So what are our possible outcomes? So we can win all right, so what's the most we can win? $4, okay? And what is the probability that we win $4? Okay, we have to roll a 5 or a 6, which means we have a probability of 2 out of 6 or 1/3, right? So this is roll a 5 or 6, okay? We can also win 0, and we can also win -5. We'll lose $5. So what's the probability that I lose 5? Okay, so this happens if I roll a 1. And so that will happen with probability 1 out of 6. Okay. And so everything else will result in winning 0. Okay. And so the total of everything, the total will have to be what? 1, right? So one of these outcomes has to happen, okay? So therefore, if I've got 1/3 here and 1/6 here, how much is left over? 1/2, right? 1/2, okay? So that's basically roll a 2, 3, or 4. Okay. And indeed, that is the answer. Okay. And our graph, if we wanted to graph this, would look like this. So at 0, we have a bar that goes up to 0.5. At 4, we have a bar that goes up to 0.333. And at -5, we have a bar that goes to 0.167. Is that okay? All right. So these are outcomes where the outcomes are what we call discrete. You either win $4 or you win 0. Like you can count the number of outcomes here. Okay, so here we have 3 possible outcomes. In other situations, we can count the other number of outcomes. In some cases, we are not able to actually count the number of outcomes. It can be something like, how tall is somebody? Okay, if I pick someone at random and I ask, how tall are you? That will technically be a random variable because the outcome that they give me is going to be a number. Okay, and if we had a very precise measuring device, right? Like I don't know, you stand on some scale or stand on some measuring thing. It is not possible to list off every single possible outcome because we could have somebody who is 5'5". We can have somebody who's 5 foot and 5.1 inches. Someone else could be 5 foot and 5.113 inches or something like that if we had a very precise measuring device. And so it's not possible to list off every single possible height that people can have. Now, probably if you ask them their height, people will round off to the nearest inch, maybe ½ inch. But, you know, there's a lot of things where the result is not something that you can just list off every single outcome, okay? If we were to measure exactly how old someone is, based on not just their age in years, but I guess he had like a decimal amount. So each day is like 0.003 or something. Okay. And so, you could have somebody who's 25 and 6 months and 4 days. And so their age would be something like 25 point, I don't know, 512, okay? And somebody else whose, birthday is like 1 day later, it would be 25 years old, 6 days, and 6 months and 3 days. And so their age would be like 25.509 or something like that, okay? We probably can't list them all off. And so in situations where we have what we call a continuous variable, the graphs have to be represented with kind of these curves or these shapes, okay? So sometimes the numeric outcome is continuous, okay? So a continuous variable can have decimals of an arbitrary length, and it is not possible to list all the values. Okay, it's just like asking how many numbers are between 0 and 1, and there's infinitely many, right? So, for example, height, you can be 5 foot. Here, let's just do like, somebody could be 65 inches, and you can have 65.1 inches and 65.112 inches, etc., etc., etc. There's infinitely many possible heights. Okay, and so to represent this probability distribution, represent a probability distribution of a continuous variable, we use graphs of, we'll call these kind of curves. And the kind of the key rule is that the total area under the curve, under a probability curve, equals 1. So we've got so here's a simple example. All right. So it says the bus comes once every 12 minutes. This is not good. All right, so okay, And so, you know, most people, when they are going to take the bus, they try to time their thing. But let's just say you arrive at a random time. You have no idea what the schedule is. You just show up at the bus stop at a random time, okay? And so the question is how long do you have to wait for the bus? So the shortest amount you'll have to wait is 0. Like you walk up and that happens to be the exact same time that the bus pulls up. You wait 0 seconds, 0 minutes for the bus, okay? On the other hand, it's also possible that, that just as you are walking up, the bus drives away, okay? And so you have to wait 12 minutes for the next bus to come, right? And then anything in between there is also possible, okay? And because you're arriving at a random time, we're going to say that any amount of waiting is equally likely, okay? So we can say anything between waiting 0 minutes and waiting 12 minutes is equally likely. And so this is going to be represented by a curve, okay? So here's kind of our number line, and it goes from 0 to 12, and the curve is just going to be flat, okay? And this means all values, so this is flat, which indicates that all values between 0 and 12 are equally likely. Okay, so in that case, all the values between 0 and 12 are equally likely. Okay, and then the other kind of, so that's one example. And I will just throw this up here, and we'll get into this on Wednesday in greater detail, and then we'll spend the rest of, so after we cover the normal distribution on Wednesday, we'll spend some time in review for the midterm. But, you know, other things might look something like this, okay? And the key, again, is that the total area is equal to 1, all right? And so IQ tests, intelligence tests, are designed so that the mean is 100. That's the average IQ that goes right in the middle at 100. And basically, this says that IQs near the average are most common, and IQs that are above are less common, and IQs that are below are less common. All right, but because it's right in the middle, about half the population has an IQ over 100, and also about half the population has an IQ below 100, okay? And so, so that's what we've got, and we will talk in more detail about this kind of probability curve and finding exact values and things like that. We'll go over that on Wednesday, and then we'll spend the rest of the time in review. Okay, good luck on your quiz today, and we'll see you on Wednesday.